Previously, we learned about bending stress. So you learned about the equation to calculate the normal stress due to bending, which is negative my over I when we have bending about our z-axis. Today, we're going to talk about two concepts related to bending stress that are just a little bit more intricate than the basic negative my over I. The first one is unsymmetric bending. So what we've talked about thus far involves symmetric shapes. So this is a few examples. And they all had a neutral axis with the moment being applied about that neutral axis. So they had a moment like this, a moment like that, and a moment like that. And they had a plane of symmetry perpendicular to that. Okay, so this was symmetry, and that was symmetry. So a little bit of restrictions on our applicability of the equation, but given that, we determined that the stress was negative my over I, where this is our z-axis, this is our y-axis, and I is computed about that z-axis. So today what we're looking at is, well, what if I have a shape, and instead of applying that moment about a principal axis, what if I just, so this is my y, this is my z, so instead of applying it about y or z, what if I have any old direction, and I want to apply a moment about that direction? What do I do now? So the way that we deal with this, if this is our moment, is we break it up into components that act about the two principal axes. So back in statics, I think you've done that before. Have you seen where you can take this moment and you can calculate m cosine of theta, where theta is this angle to the z-axis? That gives you the moment about the z-axis. Is that familiar? No? Okay, well then today you're learning. Believe me, when you take the moment and you multiply it by cosine theta, you're going to get the component that is about the z-axis. To get the component that's about the y-axis, we take that moment and multiply it by sine theta. So once we've broken it up into the two components, now we can treat it just like we did before. Each one creates separate bending stress distribution, and then we will superimpose those, right? So long as our material is elastic, we can superimpose stress states or stress distributions from different loading. So that means that the stress equation, so our normal stress in the x direction, that's our axial direction. For the moment about z, it's the same as what we had before. So this is the moment about y times y. So that's a subscript y. I want to make sure it's clear. That's a subscript y. That's a dimension y. And then I is about the z-axis. So this is the same equation we used previously, but now I'm adding some subscripts just to make it explicitly clear what axis we're measuring from and about. So we're going to superimpose that with the stress from the moment about the y-axis. I'm sorry, you know what? I wrote the wrong subscript there. That should be z. Okay, now we have the moment about the y-axis multiplied by z and divided by iy. Okay. But we need to determine whether this is positive or negative. Is it a plus sign or a minus sign? Okay, so let's take the case of a positive moment about y. That would be the way that I've shown that arrow about the vertical axis. And let's take a positive z. So positive z would put me somewhere over here. Do I want a positive moment to create a positive stress here or a negative stress here? Is that going to be stretching or is that going to be contracting? I'm talking about moment about the y-axis, so moment about a vertical axis, and I'm interested in that shaded region. Is that going to extend or shorten? Good, it's going to extend. So it should be a positive normal stress. So I have a positive moment, a positive z, I multiply those two together, and I want to get a positive stress, right? So I think I can just go ahead and put a plus sign here. Okay, so it's different than the moment about the z. When we're taking the moment about the z, we have positive moment and a positive y, which gives us this region here. But now I want that to be contracting when I have that positive moment, correct? That's why I have this negative sign. So you can either just remember that when your cross-section is in the YZ plane, it's going to be negative on the MZ term and positive on the MY term, so you can memorize that. Or you can always walk yourself through that exercise that we just did, where you say, okay, I have a positive moment, I have a positive measurement. Do I want that result to be positive or do I want it to be negative? And I'm going to put that plus or minus sign in depending on what I want. And that's typically the way that I do it, is typically my math is a positive moment and a positive y kind of regardless of which way I'm going. And then I think to myself, self, should this location be extending or should this location be contracting? And then I let that guide whether my final answer has a positive or a negative sign. But whichever way you do it is fine. One's more formulaic, one's more intuitive. Any questions?
So the I in this case would be given? Or it could be known?
It can be computed. So for this cross section is 1/12 BH cubed. Now the I, so if this is B and this is H, for the Z that is 1/12 BH cubed, but now for the Y it's 1/12 HB cubed, right?
Oh, depending on H.
Okay, so another thing we might want to be able to do is if we have this moment that's not about the y-axis and it's not about the z-axis, it's about some arbitrary axis located at an angle theta from the z-axis, we might want to know where is our neutral axis, right? Because the neutral axis will no longer be parallel to either of those two principal axes. It's going to be at some incline that we call alpha. So if we measure the angle between the neutral axis and the z-axis, that angle is alpha. Alpha is not necessarily the same as theta. So the moment about which the line about which the moment is occurring is not necessarily the same line where the neutral axis occurs. There's a special case when that happens, and we'll figure that out. So let's start by remembering, what does it mean to be on the neutral axis? What is the stress, the normal stress on the neutral axis? Good. The neutral axis tells us that the stress is equal to 0. So I can say that means negative mzy over iz plus myz over iy equals 0 when I'm on the neutral axis. I can rearrange those terms and I'm going to pull my y over z on one side of the equation, and that's equal to my iz over mz iy. So I did that. Yes, question?
That's sigma, that's bending stress, right? Not like axial stress.
Well, they're kind of the same, but let's see if I can figure out what you mean by this. bending stress is a normal stress in the axial direction. But when you say axial stress, are you thinking of like a uniform?
Like tension, I'm thinking like tension as opposed to bending.
So when we apply bending, which maybe is like from a moment or some kind of transverse loads, the stress that causes in the member is an axial tension combined with an axial compression. So portions of the member are being pulled in tension along the axis, portions are being pushed in compression along the axis. I call it bending stress. We often refer to it as bending stress, but that really just means the normal stress, the axial normal stress due to bending, so due to transverse loads.
Like when you're multiplying by z and y, are these like length?
They're the distance from the neutral axis. You're measuring the distance. So if we want the maximum stress, remember we measured all the way to the extremity of the cross section. But if we're just interested in the stress at a particular location, we would plug in that y or that z value. Okay, so the reason I wanted to pull out this y over z is because y over z, these both refer to coordinates along this neutral axis, right? So on this neutral axis, at some point, I have a y value and I have a z value. And if I divide that y value by the z value, that's equivalent, is it not, to the tangent of alpha? Opposite over adjacent? Good. So now I have alpha in this equation. So tangent of alpha equals my over mz, but mz I know is m cosine theta, and my is m sine theta. So those two aren't really independent, but rather, if I take my and divide it by mz, the m over the m reduces to 1, and I have sine over cosine, which is tangent. So my over mz is just tangent of theta, where remember theta is the angle from the z-axis to the line about which our moment is occurring. Now we have Iz over Iy. So what this tells us is we can figure out the orientation of our neutral axis because we know Iz and we know Iy. If we know the cross section, then we can compute Iz and Iy. Typically, we're given the loading, so we know the orientation of that moment, so then we can calculate the orientation of that neutral surface. From this equation, can you tell me the special case in which our neutral axis is aligned with the line about which the moment occurs? Yes, when alpha equals theta. And how do we get alpha to equal theta? What's that?
Cross sections have to be symmetrical, right?
Yes.
So Iz have to be Iy.
Iz equals Iy. So those are kind of two separate things, but they will happen at the same time. So say if you have a square cross section, your Iz and your Iy are going to be equal. If you have a circular cross section, Iz and Iy will be equal. So anytime you have Iz equal to Iy, you end up with this scenario where you have the same axis for the moment being about that axis and the neutral surface occurring on that axis.
Like if alpha is there, what is theta?
Theta is the angle between the z-axis and the line about which the moment is occurring. All right, let's do an example to help illustrate this. So if we have a member that is a square cross section, and we have a moment about this axis, so the moment is like that, and it is 850 Newton meters. We'll say this is 250 millimeters is the width dimension, and each of these are 125. So that okay, we need our axes. I'll give you the Y and the Z. That's Y, that's Z. And the angle here, this is going to be 45 degrees. And the objective of this example is to compute the normal stress at each corner. So just to keep things clear, we'll label these corners A, B, C, D. Okay, so first thing we might want to do is calculate I. In this particular case, IZ equals IY equals 1/12 B to the 4th, right? It's a square, so B and H are the same. So we're going to have 0.25 meters to the 4th divided by 12, which equals 0.326 times 10 to the negative 3 meters to the 4th. The moment about the y-axis, it's going to be 850. Now, just to be consistent, it's not going to matter, but to be consistent, I want to give you theta with respect to the z-axis, because that's how we defined theta. So that means the moment about the y-axis is going to be sine 45. That equals 601 Newton meters. The moment about the z-axis is 850 cosine 45. So that, not surprisingly, is the same value, 601 Newton meters. Now our stress in the x direction, which in this case is the kind of vertical direction, that is going to be negative mz times y over iz plus my times z over iy. All right, so if we're looking at point A, we have the moment about the z-axis, negative 850, no, that should be 601. Negative 601 Newton meters. What is the y measurement to get to A?
Negative 125.
Yeah, so we'll call that negative 0.125 meters. Now we need to divide by IZ. So that's 0.326 times 10 to the negative 3 meters to the 4th. Plus 601 Newton meters, which is the moment about the y-axis. times now I need the Z measurement. So what is this Z measurement? Is it? Should be 0.125. And is it positive or negative? Okay. Do you see that now? So if the center is here, it's 0.125 meters in the negative direction, and then divided by 0.326 times 10 to the negative third. So note that the moment about the y-axis, which is, all right, let me take it back. The moment about the z-axis, which is this one here, that's going to be causing tension at point A. You know that because you have this negative times negative, which is positive. And then the moment about the y-axis is going to be causing compression at that point, because we just have this one negative sign. And that should make sense given those directions of those moment.
Could you just, again, just go over where the C and Y are?
The axes?
No, the distances.
Okay. Z is this measurement here from the center to A. Right? And Y is this measurement. So the
125 is measuring half that distance.
it's measuring half the side of the cube. Yes, it's half of, so the whole side is 250 and half of it is 125. Maybe that's where your confusion was. It looked like the whole thing was 125. Got it. Okay, so this then gives us, if you look at that, by inspection, you can see that's 0, right? You don't even have to calculate it. So that must be on our neutral axis. And if we're clever, we'll say, point A is on my neutral axis. It's a square. So what do we know about IZ and IY? They're equal, which means the line about which the moment occurs is the same as the line that's my neutral axis. Good. Point C must also be on that neutral axis, which means I don't even have to calculate it. You know that sigma C is going to be equal to 0. And further, I know that B and D are going to be equal and opposite, right? Because this is a square and across the diagonal is my neutral axis. So B and D will be equal and opposite. So let's calculate one of them, and then we'll know the magnitude of the other. Yes?
I'm not really sure how, I don't understand how you determine whether it's compression or tension just by looking at the moment.
Okay. So when I have a moment that is positive about the Z, so I have that arrow going the way I've drawn it here about this axis, what that's going to tend to do is it's going to tend to make this member kind of curl like this, right? Would you agree with that? So when it's curling like that, I have elongation over here. So that should be this half should be positive stress because it's elongating. And then on the bottom, this part here should be contracting. So I know that I should get a positive stress at A due to that NZ. Thank you. Good. Thanks for asking. Anything else? All right, then let's continue with the stress at B. So let's try doing this one a little bit more intuitively. We know the moment about Z is 601. We're going to leave off any negative signs for now. We know the distance in the Y direction, so this distance, the magnitude of that is 0.125. We're leaving off any plus or minus signs. And then I is 326 times 10 to the negative 3. So now I look at this, I know that the magnitude is written there, but will that moment about Z cause point B to be in tension or in compression? Tension. Good, tension. So I'm going to leave this as a positive term. Okay. Now, my next term, the moment about Y is the same magnitude, 601. The distance in the Z direction to B is this value here, which we know to be 0.125, either positive or negative. And then 0.326 plus 10 to the negative 3. Okay, so now is the moment about Y, is this moment causing point B to be in tension or in compression? Tension, good. So I want this to also be a positive. And when I add those together, I'm going to get 462 kilopascals. And we know we can calculate it, but to save us some time, we know from the symmetry, sigma D must then be equal to negative 462 kilopascals. Because it's the same distance away from that neutral axis. But you could go through this calculation again if you want. The only difference would be when we asked ourselves, is that in compression or is that in tension? We would get that this was in compression and that this was in compression. So we get exactly the negative of what we have here. Yes?
So we're saying that that entire triangle, like that triangle wedge that goes from A to C to D, that's all in compression, and the other triangle, that's all in tension.
Exactly. So that's exactly what our neutral axis means. It means that on this side here, all of this triangle, that is going to be in tension. And then this other side, this triangle, this will all be in compression. Good observation.
So that's the neutral axis for the whole thing?
Yes, that's the neutral axis.
It goes across?
Yes, the neutral axis goes all the way across the member.
No, longitudinal.
No. So the neutral surface is a plane that passes all the way through longitudinally through the member. When we're looking just at the cross section, we just see one edge of that neutral surface. Does that make sense? So this is a rectangular plane that cuts across the diagonal and then all the way down through the column.
That's the neutral.
That's the neutral plane. Yeah, the axis is just the edge of that goes from corner to corner.
So these, do you just like memorize them for different shapes, or do you
No, you calculate them using these formulas.
like this?
Mm-hmm. Yeah, I mean, you can calculate that angle alpha based on this equation. We just recognized that because of the symmetry, it would be the same as the orientation that the moment is about.
I mean, that's for that orientation, so it would be different for each orientation? If the moment is applied on a different angle?
Yes, yes. Well, for this particular geometry, because it's a square, no matter how the moment was applied, you would get that that was the same line as the neutral axis. But if this were rectangular instead of square, so these two sides were not equal, then it's going to be a different orientation.
That's what I actually meant by like memorize them. Like if it wasn't like at an angle like what we were doing before, like it would have been not actually diagonal, but it would have been straight, right? Like your neutral surface, like what the very first drawings we started with.
Okay, so you're like this one?
Yeah. So like this.
Oh, you're talking about a different day.
Yeah, I mean like a different day.
Okay, so what's your question?
So this is the neutral surface, right?
Correct.
So in here, it's not diagonal, it's actually like this, right?
Right.
That's one normal conditions, no angles. Is that how it is?
That what you're referring to is having a like a horizontal neutral surface and then a moment about a horizontal axis.
Yeah.
That's when the moment is about a principal axis. But today we're talking about when the moment is about an arbitrary axis, not one of the lines of symmetry of our shape. Okay, cool. So we have another advanced topic to talk about, which is composite beams, but we are out of time. Are we out of time? No, we have 30 more minutes? Okay.
That's all true.
Take that back. We're going to cover composite beams now. I don't know why I thought class was over. All right, composite beams. So when I say composite beams, I mean that it's made out of two different materials. Okay, so our neutral axis does not necessarily pass through the geometric center. So we have, say, a rectangular cross-section where this top is material 1, and the bottom is material 2. We have y-axis, z-axis. Now, if material 1 is different from material 2, the neutral axis typically will not pass through the centroid. I have my y and z coordinate axes located with respect to the centroid, so that dot there in the middle is supposed to be the geometric center of the shape. But what you might see is that your neutral axis is going to be down here, for example. And then when you draw your strain, remember the strain is 0 at the neutral axis or the neutral surface. So you end up with this strain distribution that is not symmetric. Okay. The strain at your top is larger than the strain at the bottom. This up here being, well, both of those are negative y over rho, negative y over rho, except on the bottom, y itself is negative, so that ends up being a positive value, assuming that this is in positive moment. Yes, question?
So why is the neutral axis below? Because there's two types of materials?
Yes, because the materials are different materials.
Okay.
And it will, the reason for that will make a little bit more sense as we go along.
All right.
Yeah. And then when we draw our stress distribution, each of these materials now has a different E value. So when this strain gets multiplied by E, this first material will look something like that. And then when we get to material 1, there's going to be a different strain value. Whoops, that's not how that works. Or sorry, a different E value. So when this is E times strain in the X, we'll say this is actually E2 times strain in the X, whereas this is E1 times strain in the X. And this here, of course, is E2 times strain in the X. So within a given material, you still have that linear distribution of stress, but there's a discontinuity where the materials change. Right here, where we go from material 1 to material 2, there's a jump because the strain is the same. Right? This material is elongating the same amount because the two materials are stuck together, so they have to elongate the same amount. But the stress that's developed due to that elongation is different because the two materials have different E values. Okay, so in order to analyze these, we do what is called the transformed section method, where we replace one material with the other.
What does the negative y over e mean?
It's negative y over rho. That's the equation of strain. So we're going to do we're going to switch one material for the other so that we get an equivalent section that corresponds to the whole thing being of one material. And the new geometry should be such that the new area carries the same force as the old area. So I'll show you how we do this. We're going to let a variable n equal the ratio of the two moduli of elasticity, E1 and E2. And E1 is what we're going to convert from. And E2 is what we're going to convert to. So we're going from material 1 to material 2. So in material 1, if we look at a little dA of material, so a small area of material, the force dF acting on that small area is the stress times dA. You take a stress multiplied by an area, you get a force. And that, of course, has to be equal to the modulus of elasticity of that material times the strain experienced. That gives us the stress. And then dy dz gives us the area. So that's the amount of force acting on each little area within material 1. And we said it's important that the amount of force carried in the initial or the original configuration has to equal the amount of force carried by the new configuration. And we're going to in the new configuration, E1 is going to be replaced by E2. The strain will be the same for any particular location, but it'll have a new E value. And if it has a new E value, that means in order to keep this in equilibrium, we need to also change the area, correct? Now I'm going to instruct you to only adjust dz. So adjust dz to keep equilibrium. I don't want you to change dy, because if you change dy, now that little area no longer has the same strain value. Because if you start extending things, vertically, then the y value is changing, and now your strain is changing, and the whole thing is falling apart. But if we keep everything at the same vertical elevation so that it has the same strain value, then we can just toggle E1 and dz and come up with an equivalent area that carries the same amount of force. And so that means our dF2, well, actually they're the same, so I don't really need a subscript. dF is equal to E2 strain dy. Now our dz, we're going to say, is equal to n dz. And we know this has to be equal to E1 times strain times dy dz. So if you look at these two equations, you're going to see dy dz, dy dz. strain X, you'll notice this N has to equal E1 over E2, right?
And what does that mean, E1 to E2? Like if DF1 equals DF2, then E1 goes to
No. So what I'm saying is if DF1 must equal DF2, then changing the E value means we must adjust DZ. That's what I'm trying to say. Okay. So N being the ratio of E1 over E2, where E1 is the material we start with, E2 is the material we want to convert to. That means that is the amount by which we need to increase the width. So if I start with a rectangular cross section, remember, and I had material 1 up here on top, and now I want to change that to material 2. Depending on the ratios of E1 and E2, I'm either going to end up with something like this. Oops, that might as well be centered. Or something like that, where this dimension here is N. So if this is B, this is N times B. N times B. This is B. So when E1 is smaller than E2, N is a number less than 1, which means you're going to shrink your material in. When E1 is greater than E2, N is going to be a number greater than 1, and you're going to extend your area out. So this here corresponds to E1 greater than E2. And this here is E1 less than E2. Questions before I continue? Okay. So to transform the section, first thing we're going to do is we're going to convert that material 1 to material 2, which means changing the width from B to N times B. Now that we have a homogeneous material, we solve for the neutral axis. So if we started with a rectangle and it turns into a T or whatever that thing is, I don't know, it looks a little bit like a wine bottle to me, but maybe that's just me. You can see that your neutral axis is no longer going to be at the centroid of your old shape. Would you agree with that? The neutral axis of this T or other object is not the same location as the neutral axis of the rectangle. So that's how we get to that statement I made earlier about our neutral axis not being at that centroid. So you solve for the neutral axis of the transformed shape. Then you're going to analyze this as a homogeneous member. So that means you know that sigma x equals negative m y over I, where I is of the transformed section. So everything we do here has to do with our adjusted cross-section. Okay. Now that we have the stress distribution over this object, or over this cross-section, we can go back and calculate what the stress would be in material 1 and material 2. So we took material 1 and we converted it to material 2. So what that means is if we're looking for the stress in material 2, we already have it. That equals whatever the stress is that we computed. But if you're looking for the stress in material 1, you need to take these stresses and multiply by n. So just to make that clear, the strain in material 1 is the same as the strain in material 2, which means that the stress in material 1 over the E value of material 1 equals the stress of material 2 over the E value of material 2. Okay, would you agree those are true statements? So then I can solve for sigma 1, and it is E1 over E2 times stress 2, and this ratio is what we previously defined as n. Okay, and the last thing I have is an example. Do you want me to go over it, or do you want to try and attempt it on your own? Okay.
The one's T-shaped.
All right.
Can we take a picture?
Okay, so this example has half aluminum, half copper. And let's say that these each have a 6 millimeter height. Six millimeters, and the width is 24 millimeters. And there's a moment about the horizontal axis of 35 Newton meters. So we have a moment acting like this, 35 Newton meters. And I want to determine the maximum stress in the aluminum and the maximum stress in the copper. So the first thing we do, remember, is we need to switch the geometry. We need to change one material to the other. So it's really quite arbitrary which way we go, but the way I've solved it is by switching copper to aluminum. That means I calculated N as E1 over E2, which for copper, it should be 105. And for aluminum is 75. Means the ratios of their E values is 1.4. So the aluminum is staying the same.
You decided copper to aluminum?
Yeah, and it was arbitrary. You could go the other way. So the aluminum stayed the same, the copper got bigger. And now this new dimension is 40% larger than 24. So the 1.4 times 24 equals 33.6 millimeters. Step 2 was to solve for the neutral axis. So I want to solve for my neutral axis. And I believe we're solving from the base. So let's, once again, this is an arbitrary decision. You can calculate it from the base. You can calculate it from the top, but I think this is what I'm doing. Yes?
Does your height change or not?
No, it should not change.
Oh, yeah.
Yeah. The height should not change, just the width. Okay, so to calculate the neutral axis, which is at the centroid, we'll take y bar times area. So for the bottom shape, we have 6 millimeters times 33.6 millimeters multiplied by 3 millimeters. Okay, the first two numbers give me the area. The second one gives me the distance to the y bar, plus 6 millimeters times 24 millimeters multiplied by 9 millimeters divided by 6 times 33.6 plus 6 times 24. I got a little lazy. Those are millimeters squared. Okay, and what does that give you for the neutral axis? I believe it gives us 5.5 millimeters. So that means our neutral axis is right there.
So that goes through the centroid, right?
Yes, we calculate the centroid, and our neutral axis goes through that centroid.
Because I was gonna say that's the centroid.
Correct, yes. That's how we're getting our neutral axis location. Yeah, we did a proof a couple lectures ago that showed that our neutral axis has to be located at the centroid because that's how we make the integral of y equal to 0. Integral of y dA. Okay. So next thing we're going to do is analyze the homogeneous member. So we need my over I, which means we need I. And it needs to be about that neutral axis. So for the bottom shape, 1/12 times BH cubed. So 1/12 times 33.6 millimeters times 6 millimeters cubed. Then we have an AD squared term. So plus 33.6 millimeters times 6 millimeters times 5.5 minus 3 squared. Plus the top rectangle is 1/12 times 24 times 6 cubed plus AD squared, which is 24 times 6 times 9 minus 5.5 squared. You notice I switched the order of the 5.5. I did 5.5 minus the y bar, and then I did y bar minus 5.5. It doesn't matter. The term's going to be squared anyway. Okay, so this should give us an I equal to 4.06 times 10 to the negative 9 meters to the fourth. So I've also converted from millimeters to the fourth to meters to the fourth. Now when I calculate stress, negative 35 Newton meters. Let's see, which one do we want to do first, the aluminum or the copper? Okay, so he wants this value up here, the stress at that point. Okay, so that's going to be, y is going to be, let's see, 0.012 meters minus 0.0055 meters. Would you agree with that? Wait, why am I?
Is that the only eye we'll be dealing with for the T shape?
Yeah, there's only one eye for the cross section. The whole cross section is one eye value. Oh, you mean as opposed to IZ or NIY? Because we're only dealing with moment about one axis now. So we only need one eye value.
I mean, like, would we need any other shapes, like eye for any other shapes? No.
Not if you start with a rectangle, no. Okay. So this is the distance here. That's what I just wrote down as the 0.012 minus 0.0055. Now we're dividing by I, which is 4.06 times 10 to the negative 9 meters to the fourth. This gives us negative 56 megapascals. And there's no need to multiply by n because we're already dealing with aluminum. But now if we want the moment, or sorry, rather the stress, so that was aluminum. If we want the stress in the copper, okay, we're just gonna have to accept that that is aluminum. Okay, so if we want the stress in the copper, now we need to include N. So we'll sneak in this 1.4. Stress is 35 Newton meters. Now this distance here, we already know is the same as our centroid measurement. So it's 0.0055. But that should be a negative value because we're measuring downward. And then we're going to divide by 0.06 times 10 to the negative 9 meters to the fourth. And we should get 66.4 megapascals. Any questions? Good. All right.
I thought we just multiplied the sigma for the aluminum by the A1, E1.
To get the copper value? Yes. So you could, what you could do is you could leave out this 1.4 and calculate what the aluminum value would be down here at the bottom. And then you come back in and you multiply it by 1.4. But you have to be calculating that stress at the same location that you wanted in the end. You can't calculate the aluminum value at the top and then multiply it by 1.4 and get a value at the bottom. You have to calculate the stress value in the aluminum at the bottom, and then it converts with that 1.4 back up to being copper. Other questions? All right.
So the max stress is at the top and the bottom, for example.
Yes, your max normal stress will always be at the top or the bottom. Remember your max, next time we meet, we'll talk about shear stress, which has a different stress distribution. But for normal stress due to bending, it's always that linear distribution that looks kind of like this. You get your maximums at the top or the bottom. This may or may not be symmetric depending on what the shape is like.